All right, hi everybody. My name is Andrea Derdzinski. I'm a postdoc at the University of Zurich, and I'm going to be talking about signatures in gravitational waves from sources that are embedded in gas disks. So first, to set the stage, I'm listing several works here that suggest how accretion disks in AGN may not only host gravitational wave sources, but they can also assist in their formation or boost the formation rates. This can happen through orbit intersections of stars or compact objects in the nucleus. Over time, drag from the disk can align their orbits with the disk. They can subsequently accrete and grow. They can merge with other COs in the disk, or they can migrate. If they migrate to the central regions, they can inspiral with the central supermassive black hole. And this would lead to an extreme or intermediate mass ratio inspiral, depending on the masses. In the right mass and redshift range, this is a really powerful LISA source. And recent work has demonstrated that with Fokker-Planck diffusive calculations and accretion disk models, that this channel can actually boost the IMRI rate by orders of magnitude, potentially. Additionally, stars can form in the outer regions of an AGN disk where it's gravitationally unstable. So these stars would be born and evolve in very different environments than your typical ISM. That can lead to characteristically different population of compact remnants and gravitational wave sources. This is ongoing work that I will actually not talk about today since it's preliminary, but I can mention, like most things, your characteristics of the population and the rates will depend on things like your disk model, disk properties, and physics of fragmentation and star formation. It will not be the same for all systems, unsurprisingly. What I will talk about today is how these gas-embedded IMRIs or EMRIs are a potentially really exciting class of LISA sources. So first of all, they should have substantially lower eccentricity compared to their dynamic counterparts that form through relaxation processes in typical dry galactic nuclei. Accretion and in the disk and their accretion history in general should skew their properties as a population, namely their mass and their spin. More interestingly, though, their individual events can carry signatures of their interaction with the environment in the gravitational waveform. Now, this is because if you place a black hole in a disk, it's going to excite non-axisymmetric perturbations that will back react on the orbit and exert a torque. This torque can act to try and increase the separation or decrease the separation of the binary. This is a really tiny effect compared to gravitational waves in the LISA band, but over time it can accumulate, especially if your system has a small mass ratio, because then it has several thousand cycles while in the LISA band. And here on the bottom right, I'm showing a characteristic strain versus observed frequency. For an example, IMRI, it's a mass ratio of 10 to minus 3. And I'm pointing out just how long it can spend in the LISA band, assuming it's circular. And also how high of an SNR it can obtain, which you can see as the area under this curve above the sensitivity. So how strong are the phase shifts? We can make simplifying assumptions and estimate the deviation analytically. So any gravitational wave event has a total phase associated with it. It's basically the sum of all the cycles. You can use GR to predict this analytically for an event in vacuum. But if event is in gas or some other perturbing force, then it's going to change the total phase throughout an observational window. And how much of a deviation you accumulate will depend on basically every parameter of the system, because the system parameters, such as the mass ratio and the redshift, will determine the frequency range of the system, which determines how strong gas is compared to gravitational waves in this case. And how strong the gas torques are will depend on your environment parameters. So in this case, the AGN disk density is a huge determining factor, and other parameters like the temperature and viscosity can also affect the strength and direction of the torque. So it turns out that analytical estimates are great, but they're not always great predictors. So here I'm showing screenshots of a parameter study of simulations that I ran of 2D hydrodynamic isothermal viscous accretion disk with an embedded inspiraling point mass, really almost the simplest case you could run, but for a whole range of Mach numbers or disk thicknesses, viscosities, and mass ratios of the inspiral. And the point was to measure the torque during the inspiral and see how much it varies from analytical estimates, and then measure, for in what regime these deviations would be detectable. And I'm only going to point out one regime here, and that is what happens when you decrease the thickness or aspect ratio of your disk from 1 to 10 to 1 to 30. It's a seemingly small change in the temperature of the disk, but it actually leads to very strong differences in the torque on an embedded IMRI. This is a mass ratio of 10 to the minus 3 here as well. And here I'm showing the gravitational torque exerted by the gas, normalized by a very great analytical estimate from Tanaka et al. 2002 as a function of the inspiral separation. And you can see that in some cases you have a positive torque, in some cases it's negative, and in other cases it's seemingly stochastically variable. This means that torques have a lot of nonlinear behavior in this regime. They can fluctuate, they can change direction, and they could also be sensitive to black hole accretion and feedback, because a lot of these torques originate from gas that's quite close to the black hole. And we do not include things like thermal feedback in these simulations. So torques can be complicated, but in principle, this might be a good thing, because if we can measure the phase shift as a function of frequency or get details about this deviation, then we should be able to trace it back to disk properties, potentially. And now here I'm just showing you an estimate, assuming the average torque, neglecting variability. Okay, is it detectable on every given some measurement or normalization of the density of the disk? The idea is, unsurprisingly, a denser disk will lead to a stronger torque and a stronger deviation, but we don't know how dense AGN disks are. There's a lot of uncertainties in the disk modeling and your model assumptions, how viscosity scales with pressure. All these things change your estimates in your accretion model for disk density. And so here, if you look at the total phase shift as a function of sigma, you can see in what regime it becomes substantial or detectable. A better estimate of detectability is shown on the right, where this is basically an SNR of the deviation, or it's showing you a measure of how different your two waveforms, the one in vacuum versus the one in gas, would be. And above a certain threshold, it's in principle detectable. And so what this means is if we measure a phase shift, we could in principle trace it back to a constraint on the disk density. But how dense your disk needs to be to detect that deviation depends on the parameters of the system. So it's not all IMRIs are the same. So can we distinguish the phase shift from system parameters? This is a question that I get a lot when I talk about this, because if you had an IMRI or EMRI that you observed and it was inspiraling a bit more slowly than you expected from theory in a vacuum, then you might just assume that it has a different chirp mass, for example. But the difference is that chirp mass affects your inspiral rate as a function of frequency in a very predictable way. Gas torques do that as well, but it has a very different function of frequency. And so the key to distinguishing these effects from system parameters lies in measuring a phase shift as a function of frequency. And so while I'm not getting into those details here, I'm pointing out some very simple idea, which is, here I'm just showing your characteristic strain again, and I'm just showing how much frequency do some of these systems cover given, a range of parameters. These are systems that merge. If we catch them merging, they have the highest SNR and they chirp the most, so they're the best for distinguishing unique environmental signatures. If we catch these systems at earlier separations, they of course aren't chirping as strongly, and they also will have much lower SNR. In many cases, won't be detectable. And so right now, I just want to point out and highlight a couple of projects that we are doing here in Zurich. So this, for example, is a plot that is done by a student, Mudit Garg, who's starting his PhD this year with Lucho Meyer. And here he's just showing using analytical estimates for the waveform deviation. He's exploring a really large regime of parameter space. And this has been done in previous works that I listed on a previous slide, but here we're really revisiting this with new understandings of torque in different regimes, as well as different disk models, from thin steady state disks to massive self-gravitating disk. And we're really trying to see, we want to highlight in all the regimes, when can waveform deviations be potentially a concern or potentially a really cool opportunity to probe environments. And here I pointed out with stars, the simulations that I had shown in the previous slide. I'd shown these predicted detectability estimates. And I wrote this approximate line for where we might expect variable torques due to nonlinear gas dynamics close to the black hole. And so this is just something that I think should be investigated, because in regimes where this is more detectable, we might actually have the most, I don't want to say unpredictable torques, but torques that are the messiest. So another project that's going on is by Lauren Zwick, who's a PhD student here as well. And he has been doing great work assessing the possible additional signatures that you might get from torque variability. And it turns out that having some additional variability in torque may lead to additional dephasing or deviations in the gravitational wave in spiral that can also be indicative of torque properties. This can also lead to other interesting things. And I just encourage you to check out Lawrence's talk. It's very interesting. Just to wrap up, we should expect gas embedded sources. And I think these come with a lot of opportunities, but also potential challenges. So they should be distinguishable with lower eccentricity. Maybe there's some degree of spin or inclination alignment with the supermassive black hole, if that's measurable. Their accretion history should skew their properties of the population. Individual events could have individual unique environmental signatures in their waveform. This could vary across systems, because not only will all the system parameters be the same, but also AGN can be very different. And so we should have a way to search for generic deviations, which can then later be investigated or try to trace back to disk properties. And so I will end it there. Thank you.